Hey everybody, this is Miss Doherty. Today I want to talk to you about orbital diagrams and just reinforce some of the rules that we have for orbital diagrams and walk you through some examples. So, the previous video talked about the three rules, and the first rule you have is the Aufbau principle, where an electron occupies the lowest energy orbital first. So that means when you look at the orbital diagram, the first energy level you have is the 1s, and then you have the 2s, and then the 2p, and then goes the 3s, 3p, and 4s. And then you get to the 3D, the 4P, and the 5S. And then the 4D, 5P, and 6S. And then if you have an F orbital, you would have 4F, 5D, and 6P. Hund's rule is the easiest rule to forget about. It's the easiest rule to overlook. But Hund's rule says that electrons occupy the equal energy orbitals one at a time. And when they occupy the energy levels one at a time, they each have the same spin. And I call this the school bus rule. And the reason why I call this the school bus rule is because I played volleyball in high school. And 12 girls would take up the whole school bus because we would have one girl per seat, and we would all sit with our backs against the windows. And so this is like Hund's rule, where you have electrons occupying the same energy orbital one at a time, so one seat per electron. And then they each sit in the same spot in their respective seats, or they each have their same spin. So if we are talking about the P sublevel, the 2 P's, then your first electron is going to occupy the first P orbital. Your second electron is going to occupy the second P orbital, and your third electron is going to occupy the third P orbital. And then the Pauli exclusion principle says that electrons in the same orbital have different spins. So again, following Hund's rule, where you have one electron per orbital, your second electron is going to come in with a down spin. So you have one up and one down in the box. One up, one down in the second box. And one up, one down in the third box. So, walking you through some examples now. You have lithium with 3 electrons, and the way you find the number of electrons is you look on the periodic table for lithium, and you notice that its atomic number is 3. So neutral lithium has 3 electrons. So we start off with the 1s. We can fit 2 electrons per box. So we start with an up arrow in the 1s, and then a down arrow in the 1s. We continue with the 2s, and our third electron is in the 2s orbital. And then if we want to write the electron configuration, it's very simple. All you have to do is copy down what you have drawn in your orbital diagram. So we have the 1s. The exponent would be 2 because we have 2 electrons in the 1s. And then in the 2s, we have 1 electron. So the electron configuration would be 1s2, 2s2. So next would be calcium with 20 electrons because its atomic number is 20. So, we do the first electron is in the 1s, and the second electron is a down arrow in the 2s. Same in the 1s, sorry. In the 2s we have 1 electron up and 1 electron down. And then in the 2p we have 1 up arrow. It fills 1 at a time, so the 2p has, in the second box, has 1 electron. The 2p, the third electron in the 2p comes in as in the third box. And then you pair. So then you go down in the first box down and the second box down in the third box. The 3s, that gives us 10 electrons, so we need to keep going to 20. The 3s has 1 electron up, 1 electron down. 3p, it fills 1 electron at a time, all up arrows, and then all down arrows. And then we finally get, that gives us 18. So 19 comes in at the 4s, and 20 comes in at the 4s. And writing the electron configuration, you would have 1s2, because there's 2 electrons in the 2s, 2s2, because there's 2 electrons in the 2s, 2p6, because there's a total of 6 electrons in the 2p orbital, and then you have 3s, 2 electrons in the 3s, 3p, there's a total of 6 electrons in the 3p, and then 4s, there's 2 electrons in the 4s. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. If we take a look at carbon, we have 6 electrons for carbon. We have 1 electron in the 1s up, and then 1 electron in the 1s down. And then in the 2s we have 1 electron up and 1 electron down. And then in the 2p we have to follow Hund's rule. So we have 2 electrons in the 2p. The first electron is going to occupy the first orbital, and the second electron is going to occupy the second orbital. And that's Hund's rule. So if we want to write the electron configuration for carbon, we have 1s2, 2s2, and 2p2. Now, a very important concept is valence electrons. And valence electrons are the electrons in the outermost orbital of an atom. So, they are used in bonding, and that's the most important thing you need to know. These are the electrons used in bonding. It is the electrons in the highest energy level. So you look at your energy levels, and the energy level is the coefficients in your orbital diagram, like the 1s, the 2s, the 1 and the 2 would be your energy level. So the valence electrons have the highest energy level, so it has the highest coefficient. If you fill in it's usually the last orbitals you fill in, but if you fill in the p sublevel, and that's the last to fill, the valence shell includes that p sublevel and the previous s sublevel. If you fill in a D sublevel, the valence shell is the previous S sublevel. And what we just mean is the valence shell is the orbitals that contain the valence electrons. And if I were to ask you how many number of valence electrons, it's the number of electrons in the valence shell. So if we take a look at lithium, the last orbital that we filled was the 2s. And that is the highest energy level is 2. Therefore, the valence shell is going to be the 2s. So we would circle that. And then the number of valence electrons is just however many electrons you have in your circle. So we have 1 valence electron. Carbon, we filled the 2p sublevel and the 2s sublevel. They have the same coefficient, so that means both sublevels are your valence shell. So the 2s and the 2p is your valence shell. And so when you fill the p orbitals, the valence shell includes that previous S sublevel and the p sublevel. So the number of electrons that we have in that circle is then 4. So let's do some practice, and I'm going to take you through some practice before I assign the problems. Okay, so I want to do nitrogen. Which nitrogen has 7 electrons, and we get that again from the atomic number. So if nitrogen has 7 electrons, we're going to start with the 1s, and the first electron is an up arrow in the 1s. The second electron is a down arrow in the 1s. And then we keep filling. So that's 2 electrons, 3 electrons, 4 electrons. And then 5, 6, and 7, we have 5 as an up arrow. We have to follow Hund's rule this time. So 5 is an up arrow in the first box, 6 is an up arrow in the second box, and then 7 is an up arrow in the last box. So the electron configuration, all you have to do now is write down what you have drawn. So the 1s, we have 2 electrons in the 1s. We have 2s, 2 electrons in the 2s. And then in the 2p, we have a total of 3 electrons. And if we wanted to circle the valence shell, we filled up a p orbital. So the valence shell is the p sublevel and the previous s sublevel. So we would circle the 2p 2p and the 2s, and your valence electrons will equal 5. Oops. Well, you get the idea. Okay, and then sulfur, which has 16 electrons total. We have 1s, 2 electrons in the 1s, 2, 3, 4 in the 2s. The 2p fills 1 up in each box, and then 1 down in each box. So that gives us 10 electrons, 11, 12 in the 3s, and then 13, 14, 15, Hund's rule, and 16 goes in as a down arrow in the 3p. So to write the electron configuration, we'd have 1s2, 2s2, 2p6, 3s2, and 3p4. And the valence shell, we filled a p orbital, so the valence shell would include the p sublevel and the previous s sublevel. So then your valence electrons is going to equal 6. Then I want to do silicon. With 14 electrons. So the first 2 is an up arrow and a down arrow in the 1s, up and down in the 2s. The 2p, you have 1 up in each box because of Hund's rule, and then you pair. That gives us 10, 11, and 12 are in the 3s, 1 up, 1 down, and then 13 is an up arrow and in the first box in the 3p, and 14 is an up arrow in the second box in the 3p. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p2. And our valence shell would be the 3p and the 3s, and our valence electrons would equal 4. And now for the last one, which I want to show you how the valence shell works for a d orbital. So I want to do CR, and CR has 24. Electrons. So we have 1 up arrow in the 1s, down arrow in the 1s, 2s has 1 up, 1 down, 2p starts all up and then down, and then the 3s has 1 up, 1 down, 3p, one up in each box first, and then a down arrow in each box. And then the 4S has one up, one down. And then the 3D, that gives us 20 electrons. So then 21 in the first box up, 22 in the second box up, 23 in the third box up, and 24 in the fourth box. And that's an up arrow. So then your electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Now, the valence shell, d orbitals are tricky. If you have a d orbital, the valence shell is the highest energy level, and that's your highest coefficient. So we stopped at the 3D, but our highest coefficient is the 4 in the 4s. So the valence shell is the 4s, and your valence electrons then is 2. So that's how you do orbital diagrams. You'll have an assignment over orbital diagrams, and you have to pay attention to the directions. You are drawing the orbital diagram with the arrows. You're writing the electron configuration, so this long 1s2, 2s2, 2p6, and so forth. You need to circle the valence shell, and you need to state the number of valence electrons. So thank you very much for learning with me today. I enjoyed learning with you, in the words of Mr. P.